Okay, let's jump straight in. The world of AI, it's been moving so fast lately, especially with models that can really see and understand what's happening in images and videos, identifying objects, segmenting them out.
Absolutely. We've seen things like SAM, the segment anything model, and then SAM2, which, well, took it a step further into video.
Right, Sam too. It feels almost like magic, the way it can pick out and track pretty much anything you pointed at in a video.
It really pushed the boundaries for, let's call it general purpose perception.
Mm-hmm.
SAM gave us that initial promptable image segmentation, a huge leap. And SAM2, yeah, it brought that into the time dimension, video segmentation, tracking.
Yeah.
Much harder problems.
Totally phenomenal capability. But, like always with this cutting-edge stuff, there's a catch, right? These models are often, well, huge.
Exactly. Foundation models needing serious compute power, usually running on massive servers somewhere in the cloud.
Which is fine for some things, but what if you want that power, that instant understanding and tracking, right there on your phone, in your pocket?
And that's exactly the challenge the EdgeTAM researchers decided to tackle. EdgeTAM, that's track anything model for edge devices.
Okay.
Their goal was pretty ambitious. Take something powerful, like SAM2, a server-side model, and figure out how to make it run well, like in real time, directly on a mobile device.
Wow, okay. Putting that kind of AI onto a phone, that sounds like a massive technical hurdle. So for this deep dive, we've got the source material, the paper explaining how they did it. Our mission today is to really unpack the technical innovations that made this possible. How did they get from the server to the pocket?
Exactly. And just for context, remember SAM was the image segmentation base.
Yeah.
SAM2 built on it, added that memory bank for video, used new data sets like SAV. It showed amazing zero-shot video results. But yeah, definitely designed as a server model.
Got it. So let's start where they must have started. If SAM2 is so good for video, what was actually making it so slow on something like an iPhone? Where was the real bottleneck?
Yeah, that was step one. And it's interesting because previous work on optimizing the original SAM, it mostly focused on the image encoder.
Which makes sense, right? The encoder processes the big input image. It's usually massive.
It is massive. But the EdgeTAM team found that for SAM2, just shrinking the encoder wasn't enough. Not for getting smooth video performance on a phone anyway.
Oh, okay. So the video aspect, the tracking part, introduced a different kind of problem.
Precisely. Their analysis showed something quite specific. The new memory attention blocks introduced in SAM2 were the dominant source of latency on mobile. Not just a bottleneck, but the main one slowing things down.
Wait, hang on. So it wasn't just processing the current frame, it was how the model used its memory of past frames. That feels counterintuitive. I'd still bet on the image processing.
It does seem counterintuitive, but it's a really key technical finding in their work. So SAM2 keeps this memory bank, right? Storing densely encoded features from previous frames.
Densely encoded meaning?
Meaning feature maps that still hold a lot of spatial detail. They're like compressed representations, but they still know where things are in the frame, roughly. High-level visual info, but spatially structured.
Okay.
Now, to understand the current frame alongside the video's history, SAM2 uses these memory attention blocks. They fuse the dense memories with the current frame's features using cross-attention.
Cross-attention, okay, where the current frame sort of asks questions of the memory feature.
Exactly. But because those memory features are dense, these full spatial maps from past frames doing that, cross-attention involves a huge matrix multiplication. You're comparing every part of the current frame against this large detailed memory bank.
Ah, okay. Huge matrix multiplication. That sounds exactly like the kind of thing that mobile chips, even good ones, aren't really optimized for compared to, say, server GPUs.
You got it. The paper points out that even if the memory attention modules have fewer parameters than the giant image encoder, the way the computation is structured, that cross-attention with dense inputs, it's just not affordable for on-device inference.
They actually proved this was the bottleneck.
Yeah, they showed that if you reduce the number of memory attention blocks, or even just remove the cross-attention part within them, the latency dropped dramatically. That confirmed it was the root cause.
Okay, so a really important academic contribution there. Finding the specific, maybe non-obvious bottleneck in a complex video model when you try to run it on the edge. So how did they fix it? You can't just throw out the memory, right? That's kind of the whole point of SAM2 for video.
Right. That's where their main technical innovations really shine. They started thinking about redundancy in videos. Frames are often quite similar. So instead of feeding those big, dense memory maps directly into the costly attention blocks, they needed a smarter way to represent the memory first.
Smarter, like compressed. But without losing the crucial stuff for segmentation.
Exactly. Their first big solution, and this is a really novel piece, is what they call the 2D Spatial Perceiver. The whole idea is to compress those dense frame-level memories before they even get to the memory attention step.
Okay, a perceiver. Those are usually good at taking lots of input and boiling it down using a small set of learned queries, right? But what's 2D spatial about this one?
That's the core innovation. And it's because standard approaches didn't cut it. They found that just doing simple spatial pooling, like averaging regions, or even using a standard perceiver model, it caused significant performance degradation.
Why? What went wrong?
Because for tasks like segmentation, where you need a precise mask for every pixel of an object, you absolutely need to maintain the 2D spatial structure. The source material calls it essential. A standard perceiver treats the input more like a flat list of tokens. It might capture what's in the memory, but it loses where it is spatially.
Ah, I see. So knowing where a part of an object was in the past frame is critical for segmenting it correctly in the current frame. Location matters.
Precisely. So their 2D spatial perceiver, it's a lightweight transformer module. It uses a fixed set of learnable queries like a normal perceiver. But here's the clever bit, the structure of those queries. They split them into two distinct groups.
Two groups. Okay, what do they do?
Right. First, you have global level queries. These act kind of like standard perceiver queries. They look at the entire dense memory feature map and create a sort of frame level summarization, a global context.
Okay, the big picture summary.
Exactly. But the second group, the patch level queries, that's the really neat part. These queries have what they call 2D priors. Essentially, each query is specifically designed and trained to focus on compressing information from just one specific, non-overlapping local patch of the memory feature map.
So like one query looks at the top left corner, another looks at the top middle, and so on.
Pretty much. By assigning queries to specific spatial regions, the module inherently preserves the 2D spatial layout while still dramatically reducing the total number of tokens needed to represent that memory.
That is clever. So you get the overall scene summary from the global queries, and you get compressed local details that still know where they came from via the patch queries, keeping the spatial map intact, just smaller.
You got it. This hybrid design lets them massively shrink the input size for those expensive memory attention blocks. They report speeding up that specific bottleneck operation by about 8 times. And crucially, it maintains performance because the essential spatial cues for segmentation aren't lost in the compression. Plus, they design it as a plug-in module, so it's adaptable.
Okay, wow. That addresses the computational bottleneck. Very neat academic solution. But how did they make sure this much smaller, faster model was still accurate, performing like the big SAM2 teacher model?
Right. Speed is great, but not if the quality tanks. That's where their second main contribution comes in. A specially designed knowledge distillation pipeline.
Knowledge distillation, okay, where you train the smaller student model, EdgeTAM, to mimic the outputs or internal states of the larger teacher model, SAM2.
Exactly. Standard technique, but they tailored it specifically for this situation. The goal is to transfer SAM2 smarts to EdgeTAM without adding any extra cost when you actually run the model during inference.
Makes sense. So what was special about their pipeline?
They used a two-stage approach, really targeting the complexities of SAM2's architecture, especially its memory system. Stage 1 is an image segmentation pre-training stage. Here, they make the student's image encoder features, specifically from the F16 layer, apparently match the teacher's features using a standard mean squared error loss.
Okay, so make the student see the initial image features like the teacher does. That seems like a solid first step based on prior work.
Right, but the really crucial part for the video performance is the second stage, the video segmentation training stage. In this stage, they additionally align the features that come out of the memory attention blocks, again using an MSE loss, which they call Lemeng.
Ah, so they're not just aligning the initial image processing, they're specifically teaching the student's memory system, including their new 2D spatial perceiver, and the optimized attention to behave like the teacher's sophisticated memory system.
Exactly. That's the key insight. The paper says this ensures that memory-related modules can also receive supervision signals from the SAM2 teacher. They're explicitly teaching the compressed student model how to effectively use its memory, guided by the teacher.
That feels like a very targeted application of distillation, aimed squarely at the component they optimized.
It is, and the results show it worked. This pipeline further improves EdgeTAM's performance,
Yeah.
especially on video metrics like the SAV JNF score.
JNF, right? That's the one that combines mask accuracy and region similarity over time for video object segmentation. Higher is better tracking.
Correct. So the distillation really helps bridge the performance gap between the huge teacher and the efficient student on the core video task.
All right, so we've got identification of the memory attention bottleneck, the clever 2D spatial perceiver to fix the computational cost, and this tailored distillation pipeline for accuracy. So what's the bottom line? What kind of performance did they actually achieve?
This is the headline grabber. EdgeTAM runs at 16 FPS on an iPhone 15 Pro Max.
16 frames per second. Okay, compared to what? What was SAM2 managing on that same phone?
Around 1 FPS. Maybe slightly less.
1 FPS versus 16. That's a 22x speed up.
Yeah, it's huge. That single number really captures the scale of what they accomplished, taking something that was basically a slideshow on a phone and making it run smoothly, interactively.
A 22x speed up, while, as you said, keeping performance comparable, that's some serious optimization work. What about on, like, big server GPUs? Did it get 22x faster there, too?
No, interestingly. On something like an NVIDIA A100, the speed up compared to SAM2 was much less, around 2.3x.
Huh. Why the big difference?
Well, the paper suggests that EdgeTAM is so lightweight and optimized for these resource-constrained devices that on a massive GPU built for parallel computing, it actually gets bottlenecked by other things, like the CPU managing it, or just getting data in and out fast enough. It's too small to fully saturate the giant GPU.
Ah, okay. So that kind of validates their design choices, doesn't it?
Yeah.
The optimizations have the biggest impact exactly where they were intended on edge devices.
Exactly. It hits the target.
And the performance, you said comparable across the board.
Yeah, remarkably so. Let's break it down. For promptable video segmentation, PDS, clickbox and object, track it. EdgeTAM actually outperforms previous methods that tried to combine SAM with separate specialized tracking models like XMEM plus Raghuraman, and it achieves comparable results to the original, much slower SAM2.
Wow. Outperforming combined models with just one efficient one. What about just plain segment anything SA on single images?
If you run EdgeTAM without the memory component active, it handles image segmentation too. And it gets comparable IIU performance to both SAM and SAM2. And here's a cool detail. They found that if you give it 5 input points to specify the object, EdgeTAM, on average, even surpasses SAMH, which is a version of SAM specifically tuned for image segmentation.
Okay, that is impressive. Beating an image-focused model with something designed for video on the edge shows it's really robust. And traditional video object segmentation, VOS, like even the first frame mask.
Yep. On standard VOS benchmarks, MOSE Davis YTVOS EdgeTAM is reported as on par or surpasses previous state-of-the-art VOS models. And importantly, these are models often specifically trained on those datasets. EdgeTAM achieves this under the zero-shot setting, meaning it does well without specific fine-tuning on those VOS datasets, relying on its core SAV training.
So just to recap, it's fast, it's accurate across promptable video segmentation, image segmentation, and traditional video object segmentation, even zero shot. And it's all the same model.
That's the key takeaway. They stress it's the first model running on device for the task of unified segmentation and tracking. It handles all these different modes, PVS, SA, semi-supervised VOS, with a single architecture.
Did the paper mention ablation studies, experiments where they turned off different parts to prove they were necessary? Did those back up the importance of the 2D spatial perceiver and the distillation?
Oh yeah, absolutely. Ablations are crucial for this kind of work. They confirmed that the 2D spatial perceiver was indeed both faster and more accurate for compressing the memory compared to simpler things like just averaging spatial regions pooling.
Right.
And they also showed the knowledge distillation pipeline clearly further improves performance, adding accuracy with no extra runtime cost.
Any finer details from the spatial perceiver ablations? Did they try, only global queries or only patch queries?
They did, and the finding was using both the global level queries and the 2D patch level queries together gave the best trade-off between performance and speed. Using either type alone wasn't as good. They also found that adding some self-attention within the 2D perceiver helped.
Self-attention within the perceiver. Why?
The thinking is it helps the different patch-level representations talk to each other. So the query responsible for the top left patch can share info with the query for the patch next to it, building up a more coherent overall compressed memory.
Makes sense. It really sounds like every component was carefully designed and tested. Did they mention any downsides? Any limitations?
They did acknowledge a couple of things. One is potential differences in segmentation granularity compared to the original SAM2.
Meaning?
Meaning EdgeTAM might sometimes struggle to track very fine details consistently. The example given was like tiny bird feet, especially if those details aren't clearly visible or salient across multiple frames in the memory. It points to the inherent trade-offs you make when you compress information that much.
Seems like a potentially small price to pay for that 22x speedup on a phone, though.
I tend to agree. And they also reiterate the GPU bottleneck thing we discussed, but again, that's really just highlighting its specific optimization for Edge, not a flaw for its main purpose.
Okay, so let's try and wrap this up. The core story here is they found a specific, non-obvious bottleneck in SAM2 for mobile use.
Right, the cross-attention step using those dense memory features was computationally just too expensive.
They invented this novel 2D spatial perceiver to cleverly compress those memory features before the attention step, drastically cutting the cost while keeping the essential spatial layout.
And then they used a carefully designed two-stage knowledge distillation process. This transferred not just image understanding, but also, critically, the memory processing knowledge from the big SAM2 teacher to their efficient EdgeTAM student.
And the result, EdgeTAM. A single model that unifies different segmentation tasks, runs at a smooth 16 FPS on a high-end phone that's 22x speed boost, and keeps accuracy that's comparable to, or even beats, much larger server models and specialized trackers.
Yep, it's a really significant step forward for getting truly powerful general AI perception off the cloud and onto the devices we carry around every day.
And think about what that actually means for you, for users. Having a model this smart that can see and track pretty much anything in video instantly right there on your phone. It just blows open the possibilities for, say, augmented reality that really understands the scene in real time.
Or video editing, where you can just point at an object across multiple frames and manipulate it directly.
Yeah, or totally new kinds of computer vision apps that can do complex analysis without needing an internet connection or sending your private video data anywhere.
Exactly. That on-device capability has huge implications. Privacy, responsiveness, offline functionality.
EdgeTAM really shows that even these incredibly complex, state-of-the-art AI models, they can be optimized for edge devices. It takes clever architectural thinking, like that 2D perceiver, and smart training strategies, like the targeted distillation.
It definitely makes you wonder what other amazing AI capabilities that currently feel locked away in research labs or giant data centers might be the next to make the leap right into our hands. What kind of new challenges, but also exciting opportunities, does this rapid progress in powerful on-device AI create for all of us?
Definitely something we'll be keeping a close eye on.